Linked list we are inserting on this video. Gonna be fun. Before getting to that, two quick review problems just on our big O analysis. Given an unsorted array, what is the big O running time to access and to print the kth element of the array? Some element at a given index, in this case index k of the array. Pause the video, see if you can come up with that running time. Here's our answer. The answer is easy, it's O of 1. Arrays have direct access. We can, in constant time, instantaneously calculate the memory address, or the computer does this for us, the memory address of any given cell in that array. In this case, the cell is a generic K, and we can, in constant time, compute that kth cell, the address of it, and access, using direct access, that cell immediately and print it. O of 1 is our answer. Now compare and contrast that to the following. Given an unsorted linked list, what is the big O running time to access and to print the kth element of a linked list, the kth node of a linked list? Pause the video again, see if you can come up with the answer. The answer is O of k, where you have to define what k is defined above, it's the kth element. So we would say it's O of k because we would need to traverse at least k nodes in order to get to that kth node. Not at least k nodes, we would have to traverse those k nodes in order to get to that kth node. You can no longer directly access the values in this linked list. We have to traverse along them as we showed in that last video. So your answer here would be O of k. You could also say O of n, but it's good to define what we mean here. So n would represent the number of elements in total in this list, and we would say in the worst case scenario, the kth element is that last and final element of the list. Both answers are correct. I kind of prefer the last answer. We'd say, well, O of n, but define n. Well, n is the total number of elements, and k, that kth element could, in fact, in the worst scenario, be that last and final element, therefore O of n. One more review question, but this one in particular just from last time. We studied two Java classes. What were those two classes and what were they used for? Again, I'd encourage pause the video, see if you remember the answer here. The classes were, we first had this LL node class, and what was its purpose? Its singular purpose was to create the individual nodes of our linked list. We then had the linked list class, whose purpose was effectively to control the list. It had all of these methods that we're going to really see in this video and the subsequent videos, to insert new nodes into the list, to delete from the list, to print the list, to modify nodes in the list, and so on. All of those methods are inside this linked list class, which is used to control our list. Also, the linked list class has the ever important variable head, which has what singular purpose or single goal in life? To point to that first node. So this is just a very quick reminder of what we did last time. We had this method called print all nodes, which I'm going to quickly go through this set of animations here, showing how this worked. We first made a help pointer, which is of type LL node, because we never use head to traverse the list. We save what is inside head. What's inside head? It's the address of the first node. We save what is inside head into help pointer. And so now help pointer has access to the list. And we're going to basically traverse down our list one node at a time. We're going to check, does help pointer equal null? It does a little dance there. No, it does not equal to null. We therefore print the data value, which is 10. 10 gets printed. And what did this line of code do? It steps one node down the list, one position down the list. So help pointer, instead of pointing to 10, help pointer now points to 20, and we come back to our while condition. Does help pointer equal to null? No, it doesn't. It does a little dance there, as you see. It's pointing to an actual node. We enter the while loop, we print that node, we print 20, and we do what? We take one step down the list. Pretty straightforward, right? We then do that. We come back to the while loop, the condition. Help pointer does not equal to null. It's pointing to an actual node. It's doing this fantastic, super exciting dance. And then we do what? We print the data value, which is 50. And then we step one position or one node over, and now help pointer is pointing to null. So we come back to this while loop, and we now have our exit condition. We exit the loop because help pointer is pointing to null, and we're done. We mentioned there's so many operations we're going to perform on linked list: inserting nodes, deleting nodes, searching for nodes, and so much more. All of those operations will usually require traversing. And so that was really the foundation to understand traversing perfectly. Today is we want to talk about inserting into our linked list, inserting new nodes into the linked list. Here is our linked list class from last time. Once again, we had this private head variable, which is of type LL node, singular goal in life to point to that first node, which means what is stored inside head? What is stored inside head is the address, the memory address of that first node in memory. Here's our constructor. When you make a new linked list, of course, at that moment in time, there are no nodes. Therefore, head does not store any address. It does not store the address of the first node because there is no first node, and head is pointing to null. Here is our isEmpty method. And what's going to come down here are just going to be other methods: an insert method, a delete method, and so on. Today's all about insertion. That was super exciting. Let's look at that again. Wow. I'm silly with these animations. Here we go. Linked lists. They're normally going to be ordered, right? They're linear structures. They would normally have some type of ordering. You may have a chronological order of sorts based off of like the arrival time of nodes or insertion of when they're inserted. Maybe, but more often than not, you're going to have this key-based ordering, maybe a lexicographical ordering, such as an alphabetical ordering, right? You're going to order maybe students in a list based off of their name. Or also a key-based ordering. It's not always just alphabetical. It could be based off of an ID number or a social security number. Usually there's going to be some type of ordering in that list. Key-based is most common, and that's what we're going to be using on these examples. So nodes, when they're inserted into the linked list, they need to be inserted into their correct position based off of the key value, and that's what we're going to be focusing on. So really there's four main steps of adding a node to a linked list. Step one, make the new node. You can't add a node unless it's made. So make that new node. Step two, determine where you need to insert that node into the linked list based on its key, because it's got to go in the correct spot, right? So based on its key, determine where it gets inserted, which really means I'm going to introduce two new words here. Here's one of them. We need to identify the predecessor of that new node. What is the predecessor? The predecessor is the node that comes before the new node once we've inserted it into the list. So imagine you have 10 nodes, you insert a new node, so now you have 11. Well, after you insert that new node, the node that comes before it is the predecessor. The node that comes after it would be its successor. So when we determine this insertion point, we really need to find, hey, who's the node that comes immediately before you? That's the predecessor. And from there, we're going to make some connections. So we need to identify that predecessor. And we then need to point the new node to its successor node, the one that comes afterwards. And the last and final step is to point the predecessor node to the new node. That's a lot of words, right? So it's best to just see a visual depiction. Make a new object. Currently, let's start off, we have this list, 3 nodes, 10, 20, 50. We have a head that's pointing to 10 that's not depicted. That's okay. Here's our list. Make a new object. Well, here's a new object. It's a value, a new object with this data value 40 inside. We can clearly see that the 40 goes between the 20 and the 50 since we're inserting these in ascending order based off of that data value. Find the predecessor. Well, who is the predecessor of 40? It's the node that will come immediately before 40 once 40 is inserted. So 20 is the predecessor. We'll do a little dance with 20 so we can get a little visual. There's your predecessor. Point the new node to the successor. So we're going to make the new node point over to that successor node, which is 50. Successor is the node that comes after the new node, and it's ordering. So we point the new node to the successor node, and then and only then do we now point the predecessor node to the new node. I'm going to plant a seed for you, and we're going to answer the following question maybe in about 15, 20 minutes or so. But the question would be, why do we have to go in that exact order? And what would happen if we swapped the orders of 3 and 4? If we first did 4 here, point the predecessor node to the new node, and then point the new node to the successor node. Maybe pause, think about that for a moment, see why that may be an issue. We'll answer that in a bit. Step 2 is really to determine that insertion point, right? Identifying where is that predecessor, which means what? We're going to be traversing. We need to traverse our list until we can find that predecessor, stop traversing, make our insertion happen at that spot. So that's step 2, right? Which means we need that location of the predecessor. There's really 4 possibilities. The list could be empty, in which case there is no predecessor at all, and the new node will become that first node, and in fact, its address will get stored inside head, because what's the goal of head? To always point to that first node, or to always store the address of the first node, which means it's now pointing to the first node. Also, the new node could be the beginning of the list, meaning that new node may be, in fact, the smallest node, in which case it would still go at the beginning and it would not have a predecessor. Third case is maybe that new node is going to be the largest. It's the biggest data value that we've added and will therefore get added at the end of the list, in which case the predecessor will be the previous last node, the one that was the last node previously prior to insertion. And then finally, a fourth case is, well, it's going to not be at the front, it's not going to be at the end. This new node will get inserted somewhere in the middle. The goal for today is we're going to use sorted linked lists, right? We're going to use key-based ordering, inserting based on the correct position. Hear me clearly, that is the goal of this video, and we will accomplish that goal by the end of the video. But for the sake of ease, baby steps, if you will, we're going to do this incrementally. We're going to assume at the beginning of this video that we're only going to always add new nodes strictly to the front of the list. All nodes we're going to assume are smaller, and therefore they will always go at the front of the list. Of course, think about that. If you have an existing list of 10 nodes, and now think about if you're adding an 11th node, which has the smallest data value and therefore goes at the front, this new node added at the front of the list, clearly head is going to have to change where it's pointing to, right? Instead of pointing to the previous first node, well, now that we have a new first node, head will have to update where it points to, because head always has to point to the first node of the list. So let's go through this. Adding to the front of the list. There's really 2 scenarios. If you want to think about them, there's really just 1 line of code, by the way. I'm giving a trailer to what you're about to see, the trailer of the movie. There's really 1 line of code that accomplishes both of these scenarios. The list could be empty, in which case the new node is the only node of the list. Of course, the address of that new node gets saved into head. Or there are already existing nodes in the list, but this new node is the smallest and it goes to the front. Here's both scenarios. Insert into an empty list. Currently, head is pointing to null because it's empty. Here's a new node that needs to get inserted. After insertion, this is what we get. Super exciting, pretty straightforward. Or we're going to insert at the head, at the front of an existing list. So here we have an existing list. Head is pointing to 1 node, which in turn points to null. Always when that last node points to null, that's how it signifies the end of the list, right? So head's pointing to 4, 4 points to null. And here's this new node we want to insert with a data value 2, clearly smaller than 4. It needs to go at that first position in the list, and this is going to be our result. So let's look at this code and see what we actually do to accomplish this objective of inserting at the front of the list. From last time, here's our basic node we're using from the LO node class. They're both private. We have 2 data members, the data value, which is just an int, and then the next, which is just a private data member of type LL node. Here is the code to add to the front. Remember, we have our linked list class, we have our head, we have our constructor. Here's the code to add to the front of a linked list. It's a method, public void add to front. We're not returning anything, right? It's a void method, and we're inserting this value, some value right here. We want to insert it into the list strictly at the front. We have one line of code that accomplishes this objective, which is very cool. Let's go through this. So we're going to make this method add to front. What argument or what parameter are we sending to this method? The value we want to insert, right? This is a void method. It's not returning anything. And within this method, all we're doing is we're going to make a new node. We're going to make that node point somewhere, depending on whether or not the list was previously empty. And then we're going to save the address of that new node into head, because that new node must become that new first node. So one line of code does the job for us in its entirety. Here's this one line of code. What I'd like to do is I'm going to go through some slides here with some explanation, but I'll be to go through that quickly in a moment, because first, let's just draw this out, and then we'll probably just run through the slides, which is going to really be a duplicate explanation. So if I come over here to the tablet, here's the method. Here's that one line of code. As you are experts with, you know that this is what? This is an assignment statement. When we look at the right side of that assignment statement, which is where our eyes should always go, to the right side, we see what? This is a command. Yo, Java, make for me a new node. So here's a new node. And let's just say the value, we had value here. Let's say the value was 7. So I'm going to put here 7 is the new node. And here, I'm going to depict with an asterisk, is the next. Now this next right here has to point somewhere, right? It has to point somewhere, either to null, because the list would have been empty, or it's got to point to the previous first node. So through the power of a pause button, we have a new picture on the screen. Head is currently pointing to null, and we have, meaning it's an empty list, and now we're creating this new node. Remember, value we said had 7. Value is the 7 that we're trying to insert a new node with a data value of 7. I have created this node right here. That's the new node that we're trying to insert. Now, what do we want the next of this new node to point to? I'm depicting with an address, with an asterisk there, the next value. Well, here it says when you make a new node, so I'm going to do this. When you make a new node, well, it's got the value 7, but we have to give it that second parameter, head, which will get stored into this next right here. Well, currently, what is head? Head currently points to null, meaning head, the value that is actually stored right here in head is currently null. So what we're going to do is this second parameter, it's used as the address that gets saved into the next of our new node, which means what? It means that this next will point to null. This right here is the result of the right side of this assignment. We have a new node. The new node has a data value of 7, and the next of that new node is pointing to null. Why null? Because null is what was saved inside head over here. And so therefore null is what is saved inside that second parameter, and therefore that's what gets saved inside our next of the new node. That's the right side of this assignment statement. Well, now what does that assignment statement do? It's an assignment. We have to take whatever we did on the right and save it into the left side of the assignment statement. It says take all of that and save it into head. Now in code, what that really means is we're just going to change where head points to. So instead of head pointing to null right here, head is now, after we change that, head is going to point directly to that new node. So now let me draw another picture of a list that actually has some nodes in it before we do this insertion. Magic of pause, we have a new list. Head is pointing to a list with 3 nodes in it. Of course, that last node points to null. We are trying to now do the right side of this assignment statement. Let us pretend again that value is 7. So we're going to make a new node. Here's our new node. The data value is 7. Now let's understand once again this second parameter. That second parameter, which we showed you last time in the LL node class, it represents, in a constructor of a new node, that second parameter represents what you want this new node to point to. It represents the address that gets saved into the next right here of this new node. So we're saying, hey, for the next of the new node, take whatever is inside head and save it into the next of the new node. Well, what's currently inside head? Here's head. What is currently inside there? What's currently inside there is the address of that first node. So this says take the address of that first node, take whatever's inside head, which is the address of the first node, and save it right here into the next of the new node. The consequence of which is this new node will also point to where head points to. That new node is going to point over to that previous first node, that 10. So now we have completely executed this right side of the assignment. We created a new node. That new node has a data value 7, and the next of that new node stores the address that was inside head, which is the address of the first node, making this new node point over to that first node. So finally, we're at what? We're at the left side of the assignment. Take all of this and save it into head. The consequence of which is what? Head will no longer point to that previous first node, and now head points over to that new node that we created. One single line of code that really takes care of everything. Super, super cool. So let's come over here and see. I can probably skip through a lot of these slides because it's going to give you the exact same explanation. I'm not going to skip. I'm going to read through them, see if there's anything that we maybe missed. So we make a new LO node. We call the constructor with those two arguments. Of course, the data value, the second argument head. What is that? That's the reference that's going to get saved into that next variable of the new node. So before this one line of code executes, what did head actually point to? Well, head pointed to one of two possibilities. It pointed to the front of the list, which could have been null if the list was empty, or it pointed to the first node if the list was not empty. So if the list is empty, head currently has a null reference, right? This reference will get saved into the next of the node that we are creating. That should now make sense. Of course, that means that node we're creating, it's going to therefore point to next as well, which is fine. And that address is going to get saved into head. So head will then point to that newly created node, and that new node will point to null, this depiction that we've already shown you. The other option, if the list was not empty, head's going to store a reference to that current first node. And this reference is going to get saved into the next of the node we're creating because we sent it here as a parameter. When we made this new node, we say, hey, make the next of this new node, because this parameter, this second parameter of the constructor for LO node, it's used, one more time, it's used to get saved into the next of that new node. So we're saying take whatever's in head and save it into the next of this new node. So now what was inside head was the address of the first node. Well, we're saving that address into the next of this new node we're creating, which means this new node we're creating, it's going to point over to that first node. Finally, we take that new node and we save its address into head, the left side of this assignment, and we now get this, and we are done with this first baby step example. All of that accomplished with one single line of code, which is fantastic. Fantastic. So now we are going to move on to the second baby step, inserting at the end of a list. Step one was insert at the beginning. Step two, insert at the end. The final step is, we said, the goal for this video to insert at the correct position. Inserting at the end of the list, we're going to always assume the new node is going to have the largest data value. It has to go at the end of the list. So the method add to end is going to look a little bit different. Pause the video and think about what is going to be needed in this method in order to make this work. The answer is we're going to have to traverse, right? If we're going to have to go to the end of the list, that's a traversal. We're experts at traversal. That's the previous video. Do a while loop. Keep stepping one node over, one node over, one node over until you reach the end. but there's a slight difference in the code. If you want, even pause the video and see if you can at least try to maybe come up with some of the code. Spend 5 minutes if you like, but here's the code right here. I've highlighted the important sections. Really, everything else is just the comments, which is super important. But here we have a lot of code. Let's break down in detail what's really happening right here. So we want to traverse the entire list, and we need to traverse that list using help pointer. Pay attention to the loop for that traversal. While help pointer dot next does not equal to null, step over and keep stepping over as long as that while condition is true. What's different about that while condition from the previous while condition we saw on the basic loop that we had for just traversing a list? The answer is this dot next right here. We didn't have that previously. The condition is now while help pointer dot next is not equal to null. Why are we using this dot next? Let's think about that. What if we use the normal traversal while loop that we saw in the previous video, which says while help pointer does not equal to null, step over, step over, step over, step over. Keep stepping over until help pointer finally points to null. So why do we not have this dot next on that example, and why do we need it now for insertion? When does this loop exit? The loop exits when help pointer is pointing to nothing. Help pointer has moved off of the list. But in order to do insertion, we actually need help pointer to stop at the predecessor. It can't jump off of the list. It needs to stop at the predecessor. Now, on this example, where we're inserting at the end of the list, therefore the predecessor is going to be that last node. So we need to stop at that last node. We can't have help pointer go off of the list. Help pointer needs to stop at that last node, which is the predecessor. Of course, why? Because the predecessor in the successor needs to make some magic happen with some new references that are going to be made. So we cannot, which means we cannot do the insertion here on this code because help pointer is pointing to null. Help pointer effectively jumped off the list. It went off the list. That's a problem. It's not pointing to any nodes at all. So we need to change this where we have while help pointer dot next does not equal to null, thereby allowing us to stay on the list. We want to add a new node at the end of the list, which means after the traversal, help pointer must point to that last node, which will be the predecessor node. This last node will then point to the new node, which will come after it. So this has to be our loop. A lot of words, right? Let's make sense of this with some pictures. So here is our new loop. We have while help pointer dot next does not equal to null. Currently, let's walk through this step by step. So it just did a little dance for us. Let's do that again. While help pointer dot next does not equal to null. So help pointer is pointing to this first node, but we have to look at its next. So this first node is where help pointer points to, and here's the next. Is the next of the node we're pointing to, is it null? It's not null. So what do? We step over. Help pointer points to the second node. And now we do the while condition again. Help pointer dot next does not equal to null. Well, help pointer is pointing to 20. Its next is pointing to 50. Is this null? Nope, it's an actual node 50. So once again, we're going to step over. Help pointer is going to point to that last node. And we do this condition again while help pointer dot next. So here's help pointer pointing to node 50. The next of 50 though, it's null. So now we can exit the loop. We exit the loop and now we're ready to do the insertion. So when that loop stops, help pointer is going to be pointing to that last node. What do we do now? We have to make the connections happen, right? We have to make a new node and we need to make that last node point to this new node. We need to make the predecessor point to this new node. And here's the code to make that happen. So we already showed this, and let's actually back up and mention this right here, because although we're inserting at the end of the list, there is this one edge case where, well, what if the list is empty? So therefore the end of the list is still really you're making a new first node, right? So I have to check if head is null, there is no list, and this new node needs to get made and get saved into head. Hopefully that's clear. Else, if the list is not null, we have a list, we therefore need a help pointer We need to save head into help pointer so we can traverse. We're going to use this while loop to traverse where? To the last node, and we're going to stop at that last node. And then check this out. One line of code makes all those connections. Help pointer.next equals new LL node, and we put the value we're going to insert. Let's make sense of that line of code. Easiest with a picture. Here's that one line of code. Help pointer.next equals new LL node value. It's an assignment statement. Our eyes should always look to the right of this assignment statement. The right side says make a new LO node with the given data value. And there is no second parameter within this particular constructor we used, which means the next of this new node automatically points to null. And that's okay, right? Because we're inserting at the end, which means we want this last node, this new node we're creating, we want it to point to null because it's the last node of the list. So make a new node with its data value that we're trying to insert. Make that node, of course, its next is null. Done. We now need to save that node, the address of that new node, where? Look at the left side of the assignment. Save it into help pointer.next. Well, does that make sense? Well, if I didn't ask you to give me the code of where to save it, if I just ask a child, hey, we're trying to insert these in order, who do you want to point to 70? The child would say, well, I want 50 to point to 70. Cool. Now you, since we've already watched these videos, you already know that not only do we want 50 to point to 70, but specifically, we want the next of 50 to point to 70. So help pointer is currently pointing to that last node, right? We stopped at 50. And we want to save the address of this new node into the next of that last node. And that last node is currently referenced by help pointer. So check this out. Save the address of this new node into help pointer.next. I'll be honest, I love me some animations when they help facilitate the learning. This is a great slide for this one. We're going to save the address of the new node into help pointer.next. So I've put this blue box around the new node. Just think of that as the address of this. It represents that new node in its entirety, the address of that new node. Where does that address need to get saved? It needs to get saved into the next of 50. It's going to go right there. I love some animation. It goes right there into the next of 50. And when that happens, 50.next now points to this new node. So here's the address. This is the result of the right side of the assignment. We have this blue box, the address of that new node. The left side of the assignment says, take that address and save it into help pointer.next. And help pointer is pointing to that last node. Save it into help pointer.next. This is the result. We have now inserted that new node and we have updated the next of the predecessor. 50 is the predecessor. We updated its next. Now, boom, insertion is taken care of. We're at I say a midpoint. We're near the end, but I got to do a little brief interlude. Brain might be a little bit jello. So this one's funny. Doctor's telling you, hey, Googling doesn't make you a doctor. And we're like, but it does in CS, right? One more picture, which we have all felt. We find the bug, we fix the bug. Now we have 2 bugs. Now we have 3 bugs. We have all felt that pain. Adding nodes to a linked list. We said the goal for today is to add into the correct position based off of its key value. So now we want to do so, adding to the middle of the list or adding to the correct position, which might be the front, it might be the end if it's the biggest, but it's really going to be based off of its correct position. So we're inserting a new node possibly between 2 other nodes. This new node has to point to the successor node. And so it must point to where its predecessor was previously pointing. Then the address of the new node has to get saved into the next of the predecessor. These 2 steps are really what maintains the integrity of our list. One more time, we have this list here. Head is pointing to 4, 4 is pointing to 8, 8 points to null. We want to insert 6. It's going to go where? Between 4 and the 8 clearly. So what has to happen? We're going to go through in detail. Here is our list after insertion. But what's really going on is we're making a new node. We're finding the logical predecessor, which is the 4. 4 is going to come before the 6. We're going to traverse over to that point. And somehow in the code, we're not going to traverse to the end. We're going to traverse and we're going to stop at the predecessor. Now, if the predecessor is at the end because the new node we're inserting is the largest, well, great. But otherwise, we're only going to traverse until we find that stopping point of that predecessor. So find the predecessor, in this case, which is node 4. Now we need to point the new node to the successor. We make a new node and we first point 6 to 8, and then and only then do we make the predecessor point to the new node. At the beginning of this video, I said I'm going to plant a seed, saying that we have to go in those exact steps. We have to make a new object. We have to find the predecessor, which here's the 20. We have to point the new node to the successor, and then we need to point the predecessor to the new node. Those are the 4 steps, and I said that steps 3 and 4 have to go in that order, and I said, think about what would happen if you reversed the steps 3 and 4. If you first said, after make a new node, let's go back up, make a new object, make a new node, find the predecessor. What if step 3 was point the predecessor, point 20 to this new node? If that was step 3, what would be the consequence? Pause the video. See if you think of the answer. What would be the consequence of first making the predecessor point to the new node and then and only then making the new node try to point to what was the successor? That won't work. Why will that not work? Because in short, if we did this, if we make 20 point over here to that new node first, we make the predecessor first point to the new node, who's pointing to 50? Java has no mercy. The Java garbage collector has no mercy. If no one's pointing to 50, it will come and wipe it out. Not only wipe out 50, anything that 50 is pointing to. So you would have just lost the rest of the list from 50 and onwards. You cannot do it in that order, and that's what this says. We must first point the new node to the successor node, then and only then can we point the predecessor to the new node. Why does it have to happen in that order? What if we first made the predecessor point to the new node? What's wrong? We would lose the rest of the list. That's a problem. All of this was building up to now show you the final code. We're ready to add a new node to the correct location of a sorted linked list. And this one code is going to take care of all of the possibilities. This is the real insertion method for inserting a new node into a linked list. All of those previous methods, add to front, add to end, those are just teaching examples to build us up and get us ready to now hopefully understand this code. We're inserting a new value. That new value might be getting inserted into an empty list, or it might be getting inserted at the beginning because it's the smallest possible value. Those conditions take care of that. If head is null, we're going to insert at the front of the list, or if the value that we're trying to insert is smaller than what's currently at head, we're going to insert at the beginning of the list. And this line of code right here, well, guess what? We've gone over that in detail. This is what we drew earlier explaining that line of code, and we already understand it perfectly. Great. Else, if neither of those conditions are true, we now need to insert later into the list after that first position. So we need to traverse until we find the correct location. Anytime we're traversing, that means what? We need a help pointer. And now we also understand this while condition, because worst case scenario, we're going to insert at the end. We're not going to find our correct spot until we arrive at the end, but we don't want to go off of the list. We don't want help pointer to end up pointing to null because now you don't have a predecessor to make those connections. So we understand this while loop. We've covered that in detail. And we want to look at what's really going on inside this while loop briefly. And then here we've already looked at this line of code, which is where we make that new node. So adding nodes to the front of the list, we've already talked about this. If the head is null, or if the new data you're inserting has to go at the beginning of the list because it's the smallest value, this one set of code takes care of all of it. Both of those scenarios are taken care of by this one singular line of code, which we have exhaustively discussed. So now if the insertion point is somewhere later in the list, we have to use a help pointer, traverse over to that spot, And now we have this while loop, which we've already covered. We understand why we have that condition, the while help pointer dot next does not equal to null. If the data value at the given node is ever greater than the insertion value. So if we're traversing over along this list and the data value at a given node is greater than the value we're trying to insert, stop traversing. Stop right there, because we just found our insertion spot. We found the predecessor. Break out of this while loop, stop traversing, you found the predecessor, and that is your goal, right? So this is really what's happening inside this while loop. At every step of the traversal, we're checking, hey, we're looking at help pointer dot next, its data value. Hey, that next node after help pointer, is it bigger than where we want to insert? If it is, we have to stop our traversal. We break out, and now we're ready to traverse. Now, if we didn't break out, if that wasn't the case, it was not bigger, of course, we know this line of code perfectly. Keep traversing. Step one node down our list. And then finally, we get to this line of code, which is where we're now going to make our new node and set up the connections. Make a new node with a given value. Make the new node point to that successor node, which is help pointer dot next, and then save that result into help pointer dot next. Let's make sure we understand this. So let's say in this case, we're trying to insert that node 40 again, find the predecessor. 20 is clearly the predecessor. Make a new node. Here's the new node. And make this new node, think about this, make this new node point to 50. That's the third step, right? The next of this new node, it has to point over to the 50. Well, who knows where the 50 is? At this moment in time, pause the video. Who knows where the 50 is? The answer is, well, the only person who knows where the 50 is the 20. In specific or in particular, it's the next of the 20. Cool, cool. Who knows where the 20 is? Only help pointer. So how do we access this next right here, the 50? We say help pointer, which brings us to 20, dot next, which brings us over to the 50. We need to take the address of the 50 and save it into the next of the 40, right? So make a new node, we did that, but we need to make this new node right here, we need to make it point over to 50. So we need to get the address of 50. So in short, where's the address of 50? It's stored within the next of 20. How do we get that? Help pointer brings us to 20. Dot next, right here in help pointer dot next is the address of 50. Take that and save it into the next of the new node, which is why if I back up, you see when we make a new node, what do we save into its next? We save help pointer dot next, which was the address of that 50 right here. So the next of the new node, it gets the value from help pointer dot next. So now the new node is pointing over to the 50, and the final step is save the address of this new node into the next of 20. Well, where's the next of 20, or who has access? Help pointer points to the 20, and here's the next. Help pointer dot next is how you finally make that connection happen. That's it. You might need to hear some of those things again. No problem. I won't repeat it, but you can always back up, pause the video, listen again, reach out, ask questions, leave a comment. Was that awesome? I don't know. You tell me, was that awesome? Our demotivator, blame. The secret to success is knowing who to blame for your failures. It has been fun. Take care, everyone.